So in the last video, we discussed about some basic introduction that what do we mean by static timing analysis. So when we are analyzing the timings in the synchronous timing domain, then we are often interested that what the maximum frequency I can get for the clock, or in the reverse way I can also say that let's say I have the goal of designing a circuit which runs at certain frequency, let's say 1 gigahertz. So earlier we were talking that we have designed the hardware, these flip-flops, these CLVs. Now in the previous video I said when we have designed these hardware, then we are taking decision about the clock. That I mean that if you have designed the hardware, then what's the minimum time period now you will be needing to send the data from sender to receiver. Now in the reverse engineering way, we can say that, okay, we have the goal or we have the need that I need to run a certain hardware at 1 gigahertz. So in the sense we have fixed the time period is equal to 1 nanosecond. Now you have to design the CLV such that it will not violate the rules of setup time and the hold time. We call that setup time violation and the hold time violation. Or in the simpler manner, we can say that the 1 nanosecond time period would be efficient and would be enough to send the data from sender to receiver. So we can discuss this problem of sending the data in the both ways, that either we have to design the CLV given that we have fixed the clock time period, or we have designed the CLV and you have to design the clock now. You have to generate the clock now on the basis of fact that what's the minimum time period this hardware is taking. So we will discuss this problem that we have designed these CLVs. They are taking certain delay to process the data from input to the output. Now we need to calculate that what's the minimum time period we need to have for the clock so that we can effectively send the data from this sender flip-flop to this flip-flop, okay? And later this latched data receiver can get and can store into that on the flip-flop or some sequential element. Now so we said in the earlier video that let's say data has come at this point when the rising edge of the clock 1 comes, and remember clock 1 and the clock 2 are the same. We have no skew and the jitter. So for simplicity we are avoiding these timing uncertainties. We also call them timing noise. So for sake of simplicity we are taking the ideal clocks. That means from clock 1 to clock 2 there is no delay. These paths are ideal. So clock 1 and clock 2 are at the same frequency and there is no skew between the clock 1 and the clock 2. Now let's say the data has come at this point. Now when the rising edge comes for the clock 1, this data would be sampled and this D flip-flop would be taking some T clock to Q delay. We call TCQ. But now here we are concerned about the worst case analysis. What I mean by worst case analysis, that in the worst case, how much time this unit is going to take to sending the data from this flip-flop to the receiver flip-flop or in the second flip-flop. So worst case analysis means the maximum time which is going to taken by this data from this flip-flop to this flip-flop, so that we can decide, okay, this is the maximum time which is the data is taking, so at least this amount of time period I need to have for my clock. So remember, we are calculating here the minimum time period which I will be needing to successfully sample the data at first flip-flop and latch the data at second flip-flop. So for getting the minimum time period, I need to have the maximum time which is taken by this D flip-flop, this CLB and the second D flip-flop. So when the data will be sampled at this clock 1 rising edge, at the output it will be needing some time to come at the output. So we call it the clock to Q propagation delay, and when we are talking about the maximum clock to Q propagation delay, we call it propagation delay. So clock to Q propagation delay. So the maximum time taken by this D flip-flop from clock to Q or from clock to the output, we will be having clock to Q propagation delay TPCQ. Now once the data has arrived at the output of this first D flip-flop, this data would be processed by CLB and would be taking TPD CLB. That means, again we discussed in the previous video that CLB also has the contamination delay and the propagation delay. CLB means combinational logic block. So this is some combinational hardware. So the maximum time be represented by the propagation delay and the minimum time we represent the delay by contamination delay. So TCD and TPD we have discussed earlier. So this CLB would be taking the maximum delay of TPD CLB, whatever the delay of this CLB is PD, that propagation delay. And then we said this D flip-flop would be capturing this arrived data at this second rising edge. So in order to capture this data effectively, we need that data must come at least T setup time before this rising edge. Okay. So if you want to sample or capture the data at this rising edge, we need to have the data come by at least this point. So we need the T setup time margin at least before this second rising edge. So how much time we need before the second rising edge of the clock to arrive? We need at least T PCQ, clock to Q propagation delay, taken by this first D flip-flop. Then the data will be processed by CLB. This will be taking TPD CLB, maximum delay, which we represent by propagation delay of this CLB, and at least T setup time we need before the second rising edge. So this much of margin we need. So this much of at least time period from this rising edge to second rising edge we would be needing. So my T clock must be greater equal to this expression we got here, is not it? So at least this much time period I need to have if my second rising age is coming after this, or in the sense if we have the larger time period compared to this expression, do not have any problem, but at least this much of time period we will be needing so that we can effectively capture the data. So there are two terminology we often use. We latch the data here and we capture the data here. So latching of the data at first flip-flop and the capturing of the data at second flip-flop. So this is the terminology which is being used in the VLSI domain. So we got the expression for minimum time period. From this expression you can get what's the maximum frequency I can get. So the minimum time period is this. So F max will be 1 upon this time period, TPCQ plus TPDCLB plus T setup time. So this much of the maximum frequency. So frequency, this is the maximum frequency, or in the sense generally I can call it F is less than equal to this. Okay, so this is the maximum frequency expression. So in the next video I will be talking about the hold time and the expression for the hold time, and then later in the videos we will be including the timing uncertainties in these expressions, because this expression is for ideal clocks where we do not have any skew between this clock 1 and the clock 2. So we will be including the skew and the jitter. These are the two major timing uncertainties. So stay tuned. Thank you.